Colleagues and participants, I am teacher of Bukhara State University, Sardar Karamatov. It is our great pleasure to present our research entitled Synthesis, NMR and IR Spectroscopy, DFT calculation of Schiff bases derived from Benzalacetone and Benzalacetophenone with Alanine. This work has been conducted by our team from Bukhara State University. Sorry for my pronunciation. Introduction. Schiff bases, also known as amines or azomethynes, represent a fundamental class of organic compounds characterized by the presence of a carbon-nitrogen double bond formed through the condensation reaction between primary amines and carbonyl compounds. These compounds have garnered significant attention in medicinal chemistry, coordination chemistry, and material science due to their diverse biological activities and structural versatility. The incorporation of amino acids into Schiff-based frameworks has emerged as a promising strategy for developing bioactive compounds with enhanced pharmacological properties. Amino acids, being natural building blocks of proteins, contribute to the biocompatibility and biodegradability of the resulting derivatives while potentially improving cellular uptake and the target specificity. Benzalacetone and the benzalacetophenone are AB unsaturated carbonyl compounds that serve as excellent precursors for Schiff base synthesis. These compounds possess extended conjugated systems that contribute to their biological activities and spectroscopic properties. Materials and methods, chemicals and reagents and instrumentation. All chemicals and reagents used in this study were of analytical grade and employed without further purification. Benzalacetone 99% purity and benzalacetophenone chalcone 97% purity were used as the starting aldehyde components, while Alanine 99% purity served as the amine source in the Schiff base formation. Absolute ethanol was used as the solvent throughout the synthesis, and the glacial acetic acid was added as a catalyst to facilitate the condensation reaction. Anhydrous magnesium sulfate was employed as a drying agent to remove residual moisture from the reaction mixture. For instrumental analysis, a four-tier transform infrared spectrometer operating in the range of 4,000 and 400 centimeter was used to confirm the functional groups in the synthesized compounds. The melting points of the solid products were determined using a digital melting point apparatus via the open capillary method. A rotary evaporator was utilized for solvent removal under reduced pressure, and all weighing procedures were performed using a high precision analytical balance with an accuracy of plus and minus 0.0001 gram. Synthesis of Schiff bases. A solution of benzalacetone 1.46 gram and 10 mmol in absolute ethanol 25 ml was prepared in a round bottom flask. Alanine 0.89 gram and 10 mmol was added to the solution, followed by 3 and 2 drops of glacial acetic acid as catalyst. The reaction mixture was refluxed for 4 to 6 hours at 78 degrees Celsius with continuous stirring. The progress of the reaction was monitored by thin layer chromatography (TLS). After completion, the reaction mixture was cooled to room temperature and concentrated under reduced pressure. The crude product was purified by recrystallization from ethanol to yield the desired Schiff base as yellow crystals. Expected yield 25 to 85% molecular formula C13H15NO2 molecular weight 218.26 gram mole. Results and discussion. Both Schiff bases were successfully synthesized through conventional condensation reactions. The reactions proceeded smoothly under mild conditions, with good yields obtained for both compounds. The formation of the Schiff bases was confirmed by the disappearance of the characteristic NH2 stretching bands of alanine and the appearance of new stretching bands in the IR spectra and the new characteristics NMR shield. H1 and C13 NMR spectral analysis of Schiff base. H1 and C13 NMR spectroscopy serves as a vital tool for elucidating the carbon skeleton of organic compounds, particularly in confirming the presence and chemical environment of carbon atoms within Schiff. H1 NMR spectral analysis of BASC. The H1 NMR spectrum of the BASC Schiff base reveals well-resolved chemical shifts that are consistent with the structural features of the molecule and confirm the formation of the imine linkage between the benzalacetone and the amino acid alanine. A downfield singlet at 12.01 ppm corresponds to the carboxylic acid proton minus COOH, strongly deshielded due to hydrogen bonding and electron withdrawing effects from the adjacent carbonyl group. This peak is a diagnostic signal confirming the presence of the free acid moiety. The H1 and the C13 NMR spectra of benzalacetone alanine and benzalacetophenone alanine Schiff bases exhibit characteristic chemical shifts that are in excellent agreement with their proposed molecular structures. IR spectral analysis of Schiff base. Infrared spectroscopy remains one of the most reliable analytical techniques for identifying functional groups in organic compounds. In the present study, the IR spectral profiles of BASC and the BPSC Schiff bases were carefully examined, providing valuable insights into their structural features and the functional group composition. IR spectral analysis of BASC. The IR spectrum of the BASC Schiff base exhibited a broad absorption band in the range of 2,300 and 3,500 centimeter, which is characteristic of the OH stretching vibration associated with the carboxylic acid group. This broadness may be attributed to the presence of intermolecular hydrogen bonding. aromatic and aliphatic C-harsh stretching vibrations were observed at 3,100 centimeter and 2,800 and 3,000 centimeter respectively, confirming the presence of both aromatic rings and aliphatic chains within the molecular structure. IR spectral analysis of BPSC. In the case of the BPSC Schiff base, a similar spectral pattern was observed, with certain variations in band positions and in intensities. The OH stretching vibration appeared slightly shifted to the 3,200 and 3,400 centimeter region, again indicating the presence of a carboxylic acid group possibly engaged in hydrogen bonding. Aromatic and aliphatic C-harsh stretching vibrations were located at 3,000 and 3,100 centimeter -1 and 2,900 and 3,000 centimeter -1 respectively. In conclusion, the HOMO-LUMO analysis of the Benzalacetone Alanine Schiff base confirms successful conjugations between the aromatic and the imine systems, demonstrates moderate reactively, reveals defined donor HOMO and acceptor LUMO domains, and suggests that this molecule is suitable for further exploration in pharmacophore modeling and interaction with electrophilic or nucleophilic targets. Conclusion. This study presents the successful synthesis and characterization of novel Schiff bases derived from benzalacetone and benzalacetophenone with alanine. The NMR and IR Spectroscopy analysis confirmed the formation of the desired compounds, with characteristic absorption bands corresponding to the azomethine group and other functional groups. In summary, while both complexes exhibit comparable electronic characteristics, BPSC demonstrates slightly greater reactivity and electrophilicity due to its lower energy gap, higher softness, and enhanced charge accepting capacity. These distinctions may influence their performance in subsequent chemical or biological applications. Furthermore, the electrophilicity index, which indicates a molecule's capacity to accept electrons, is higher for BPSC 13.41 eV than for BASC 12.228 eV, suggesting that BPSC may function as a more potent electrophile. Lastly, the maximum amount of electronic charge species can accept is also greater for BPSC 3.933 than BASC 3.573, reinforcing the idea of enhanced electron accepting ability in BPSC.